today. It's the last one, but not the least. There's only two people in the session today. They're both presenting from the University of Dundee. I myself, Dr. Thomas Jones, I'm a lecturer in engineering at Dundee, so this is actually the Dundee session today. First person speaking will be Sean. He's one of my PhD students. And yep, so if you just go up to the podium, Sean, and begin in your own time. Thank you very much.
Right, so yeah, I'm Sean Douglas. I'm a PhD candidate in Material Science and Engineering Research Cluster. So yeah, today I'll be talking about inkjet printing of organometallic non-particulate platinum inks. So I'll try and break this down onto what drop-on-demand printing is, and then discuss the printability of the ink, the previous work that's been done within the team, some results that I've got from my research, and the application that I'll be focusing on in my PhD thesis. So start with, at the top right, that is the picture of the Dymatics materials printer that we have, and you can see the stage, and above that the cartridge goes over it, the same as your printer at home. And on the left, that wee white thing that sticks out, that's the cleaning station that can clean the cartridge just to keep the cartridge going for longer. And on the far right, which you can't quite see, but it is there, is the drop watcher. And this is where we can do some cool stuff with the droplets in the nozzles. We can it's a camera that lets us see the nozzles on the cartridge, and on the cartridge is 16 piezoelectric nozzles. And through this camera we can see which ones are working. So some of them can get blocked, some of them can not jet correctly. So when we see the droplets, we want to make sure they're going in a straight line, not off at angles. And we also want to make sure the velocity is within a optimized zone of about, I think, 6 to 9 meters per second. And we can change that speed by changing the voltage that is applied to each nozzle. And on the bottom left there is an illustration of how we can create these droplets using a waveform which is applied to the piezoelectric nozzles. And this waveform can be broken down into 3 sections. The first, which is complete relaxation of no voltage is applied to the nozzle, which creates a low pressure, pulls the ink into the nozzle. We ramp the voltage up to 100%, which we set dependent on the velocity that we want. That pushes the ink out, and we gradually reduce the voltage to break the droplet into a teardrop, and then reduce it further to snap it off so we get a single droplet. It's important to control that so that we don't get satellite droplets behind the main droplet, as that will cause splashing on the deposit, which can cause deforms. On the bottom right, there's just a demonstration of a complex structure that we can print with the printer, with the platinum ink as well. So the printability of an ink is an illustration of how, if the ink is printable. So it's a measurement of the Reynolds, a ratio between the Reynolds number and the Weber number, and which is so both these, the Reynolds number and the Weber number, are dimensionless numbers, which is a ratio between the internal forces and either the viscosity of the solution or the surface tension of the solution of the ink. And on the right here, we've got 2 images that are an illustration of the printability. So we want to be in the center area that's kept white there. So we've got two on the left there, and the right we've got the sort of limits that we want. So the Z is the printability, it's another dimensionless number. We want to be between 1 and 14, which we measure with that equation. That X is where our ink is, so it's in the printable region. The and the top and bottom regions, the limits can be controlled by its velocity. So if the nozzle voltage is insufficient, then it won't jet. You won't get a droplet. If it's too fast, too much, the voltage is too high, there'll be too much force as the droplet hits the deposit, and it'll splash, and you'll get deforms. On the right graph there is another printability measurement of what happens as the droplet lands on the substrate. If the spreading of the droplet is controlled by impact-driven forces or capillary-driven forces. Our ink, for drop-on-demand printing, which our printer is, you want to be within the impact-driven, which means as it hits the substrate, it spreads. Its maximum spreading is defined by those parameters, and then it'll follow by a bit of relaxation, which will eventually be by capillary-driven. But initially it's impact-driven, which is the range you want to be in. And then those numbers are values I measured by measuring the viscosity, density, and surface tension of the ink, which gives that Z number 2.35, which is between the 1 and 14, so it's a printable ink. So this ink was previously optimized by a previous PhD student. And how he optimized it was by creating blank inks, which is the solvent without any platinum. That behaves the exact same way. So he created blank inks with different concentrations of a viscosity additive to change the viscosity of the ink, and then printed it and watched what ranges of nozzle voltages you could print within, and then the temperature at a single nozzle voltage to determine which concentration was the most optimum. So from there, I've then taken that ink and I'm printing some deposits, and this is just a simple test of printing a 10 millimeter by 2 millimeter strip of line and changing the drop spacing. The drop spacing is the distance between each droplet. As we print so many droplets in a line, we can define the distance between each droplet. Turns out defining this distance between each droplet can control the porosity of the deposit, and as I increase the drop spacing, the porosity increases, and we can see how this affects the edge definition of the deposit, the size of the coffee rings that we get, and the electrical properties. What I found interesting was the thickness at the center of the films stay the same depending on how the drop spacing, as it's depositing more solution, more ink, so you'd think that might have effect. Turns out it doesn't really have much effect, but it does seem to have an effect on the size of the coffee rings, as with the smaller drop spacing, the ink seems to move to the outside, so we get these coffee rings, which keeps the center at the same thickness. And you can also see the effect on the electrical properties, where we can go very dense and get very high conductivity, very low resistivity, and then we can increase the porosity and get lower conductivity as well, which is cool. So the application I'm applying this to is dye-sensitized solar cells. And if I just talk about what a dye-sensitized solar cell is to those who don't know, a dye solar cell is a solar cell that has a mesoporous semiconductor layer, which is coated in a dye sensitizer. The dye sensitizer absorbs light, which then transfers the electrons to the semiconductor, which is then diffused into the external circuit, then returns through the cathode, which is what I'm printing with the platinum, and then the platinum acts as a catalysis to the reaction to transfer the electrons back to the electrolyte, which then reduce the oxidized dye molecules back to its original state, so we can restart the solution, the reaction, the system. So there's a few things that I'm looking at with the platinum in terms of the thickness, how the thickness will affect this reaction, and also the porosity. As we see in the previous slide, when we change the porosity, we reduce as we increase the porosity, we reduce the conductivity, but we could also potentially increase the reaction rate with the electrolyte. So it's an interesting thing that I'm going to be having a look at. I think I might have been a bit quick, but that's it. Talked a bit quicker than I thought.
For that presentation, Sean. It was about on time, I thought. Are there any questions from the audience?
Hiya, good work, Sean. I think it was slide 8. I think you had some 2D profiles. Yeah, sorry, it was slide 9. You know, if we look at those profiles in the middle, so say the one in the middle and that one on bottom there, yep. Is that a function of where the next droplet is, or are those independent droplets?
So they're surface profile measurements measured with a DECTAC lab. So that's after annealing. So that's the platinum film. That spike will be dust.
Dust?
Yeah, that big spike will be just a bit of dust.
Oh, no, so you know it's kind of got two shoulders on them.
Yes. So what we're observing there is the coffee ring effect. So when you deposit the solution, like a coffee cup, you find a ring on the outside. Mm-hmm. This is usually a sign that your solution is particulate, as the particles, with the capillary motion, the particles move to the outside. Our ink is supposed to be non-particulate, mm-hmm. but we still observe this.
So sorry, the question was is there another droplet adjacent the one that you've pictured there, or are they just
on the bottom one at the edges, at the very edge? So sort of
on any of them so that represents one droplet. Is there another one close by, or are they just on one piece of material, nothing next to it?
No, that's 2 millimeters white. So that's the full deposit. So I deposited a 10 millimeter
droplet on droplet on droplet.
So that is measuring all the way along. So we deposit every 20 micrometers.
Yeah.
So if that's 2 millimeters, we're depositing.
Sorry, got you. Okay. And one last one, if I could. Do you think the surface characteristics of what you're depositing on your substrate play a role?
Sorry?
The surface characteristics of your substrate, what you're depositing on, do you think they play a role in influencing what you're seeing?
Yeah. So the surface tension between the droplets and the substrate will affect the sort of edge definition.
Yeah.
Yes.
So it's not just about ink refinement. You're bearing in mind the substrate as well. Is that the case?
Yeah.
Okay.
Any other questions? Right. So what do you do to the substrates before you print?
Clean them.
You clean them, yeah. So that has an effect on the surface properties. What's the drop spacing, and what does that mean as a concept? You've mentioned drop spacing and porosity. What does that mean?
Yeah, so so the drop spacing is so in drop-on-demand printing, you drop, so this process drops a single droplet, and that does it 5 kilohertz a rate. So that, and then we define twin drop spacing, which is 20 micrometers. So it drops at a rate of 5 kilohertz, but the drop spacing is the distance between each droplet.
Of about 20 microns, as you said.
Yeah.
So they overlap on top of one another.
Yeah.
Yeah. Do you know the diameter of the droplet, an individual droplet?
45
About
micrometers.
45 micrometers, yeah. Okay. You mentioned voltage and piezoelectric. What does that mean? How are they related? What's that got to do with print speed, droplet speed?
So the voltage that you apply to the piezo element is controls the force, the pressure that is applied to the droplet and the ink that's within the nozzle. So this process of the waveform, you reduce it to 0, which creates a low pressure, draws the ink into the nozzle. You ramp the voltage up to 100%. You set that voltage dependent on the velocity you measure afterwards. That pushes the ink out at that velocity.
Okay, so what happens to the piezo material when you apply a voltage across it?
It relaxes. You can see like a red line.
Right. So you're changing the volume of the internal cavity.
Yeah. To create a low pressure to draw in, and then you ramp it up, high pressure pushes it out.
Okay, all right, thank you. Are there any other further questions? Okay, well, thank you very much again, Sean. So if Magic can come up now. He's going to give a talk on low carbon concrete, reviewing the future assessment technology for service life and fire resistance. In your own time.
Good afternoon, everyone. My name is Maciek Joswick, and I'm a third-year PhD student in concrete technology and structural engineering at the University of Dundee. I am here today to talk to you about, to tell you a little bit more about my project. The title of the project is, as Tom just mentioned, Low Carbon Concrete, Future Assessment Technology for Service Life and Fire Resistance. But before we dive into the details of it, I'll just give you a little bit of a background on concrete. Concrete is the most consumed man-made material in the world, second only to water. And as you can imagine, its contribution to the overall sort of global CO2 emissions is quite substantial and currently sits at around 8%. Concrete is a wonderful material. It's cheap and it can be easily adapted to extreme and challenging environments. And as a result, we'll probably end up using it for forever and a day. And therefore, it is very important to put all the efforts into its decarbonization. This can be done in basically two ways. One would be to make the process of manufacturing more sustainable and more efficient. And another way would be to try and displace the most CO2 heavy material within concrete, which is Portland cement. So Portland cement has been around for nearly 200 years now. It gives us the desirable performance and durability of concrete, and it's still probably the most widely used cement in the industry for these very reasons. Then we have, well, the only problem with the Portland cement, as you can see on the table, is that the manufacturing process is quite energy intensive, which contributes to that type of cement being the least sustainable out there, essentially. Then we have low carbon alternatives. of cementitious materials, which are granulated blast furnace slag, or GGBS for short, fly ash, and limestone fines, which are all waste byproducts of the, well, essentially waste byproducts of steel production, coal-fired power stations, and limestone processing, respectively. And therefore, you can see that the CO2 footprint is associated with these materials is quite low, because it's associated with the actual primary product rather than the waste byproduct. Okay, but what do we consider to be a low-carbon concrete? A conventional concrete would look something like this. So we've got 85% of Portland cement with a little bit of addition of 15% of limestone. So technically, anything below 85% could be argued to be a low-carbon concrete. Now, in this project, we tried to go as low, as reasonably low carbon as we potentially could, without compromising the performance and durability. And so we ended up pushing the PC replacement up to 50 or even 60% PC replacement with GGBS, limestone, and or fly ash. In conventional concrete, after being cast, requires at least 28 days 28 days of curing at 20 degrees Celsius to reach its full maturity. When it comes to low-carbon concrete, and as we just said, low-carbon concrete utilizes the low-carbon cement alternatives, which are often related to as slowly reacting cements, due to the fact that instead of 28 days, now they need 90 days to reach its full maturity. So this is particularly an issue with the so-called pre-construction concrete testing phase of a project. When we have got a project, and before we use it in situ, we have to test it in labs for particular environmental exposures. So the typical time frame would be 28 days for the sample to mature, and then plus the required time for the for the given test to be performed. Now, with low-carbon concrete, we need to extend that sort of time frame by 8 weeks, or 62 days, roughly 8 weeks, and then which is basically just far too long for the industry, because now we're adding additional time, and then time equals money, as you probably all are aware. Right, so what if we came up with a method of trying to accelerate, to minimize that 90-day period to the minimum? So essentially trying to accelerate the maturity process without compromising neither performance nor durability. And that very research question sort of evolved to the aim of this project, which is to develop a rapid and reliable test method, or methods, for low-carbon concretes to assess performance and durability. One of the ways of accelerating the maturity of concrete would be to increase the temperature of curing. This is not a new concept. Precasters have been doing that for ages. What we've done, we've decided to put a spin on it. So essentially, for the first 3 days, we cured it at 20 degrees to let the initial chemical reactions to happen, and then we add we then put the samples in 50 degrees Celsius for X number of days to essentially match the strength of the 90-day standard cured samples. So what we know is that the performance and durability are somehow interconnected through the mechanical properties of concrete. So there is a good chance that if we manage to match the performance, the strength, by curing at 50 degrees, there is a good chance the durability will still be unchanged to that of a 90-day standard cured samples. And it will become more clear once I explain these graphs a little bit more. So the graphs are showing compressive strength gain against curing time. The blue curves represent the standard curing process of low carbon concrete. The red curves are representing the accelerated curing process at 50 degrees for the very same components, the identical samples, just cured at different, one is cured at 20 degrees and the other is cured at 50 degrees. And you can easily see that at 50 degrees, the strength develops much more rapidly rather than when cured at 20 degrees. And then you can see as well, if you look at the dotted line, that the 90 days strength now is achieved within the first 12 days of 50-degree curing. So as I said before, there's a good chance that if we match the strength performance, that the durability will be unchanged. So what is left to do now is to compare the microstructure of the 12-day cure at 50 degrees with the 90-day standard cure at 20 degrees samples, and to see whether they whether durability matches. And then to assess durability, we have to look at the mechanical microstructure of the sample. So we have to really look up close the concrete, measure its porosity, and trying to understand of what's going on inside of it. So like I said, yeah, the next step would be to investigate the physical and chemical composition of 12-day samples cured at 50 degrees and compare it with the standard cured 90-degree samples. It is probably worth to mention now, and this is what I'm doing now. So this is some of the raw data that I've managed to collect over the past few weeks. And it's probably important to mention at this stage that the underlying microstructure and the chemistry of concrete are immensely difficult to investigate, and due to the multi-composite nature of concrete. The idea is that there's no single test that will show us what the microstructure is like within concrete. So what we're trying to do is to do as many microstructural tests as we possibly can to show us the microstructure from different angles of such material. To sum up, slow reactivity of low carbon concrete is a well-recognized practical issue. Equivalent strength for heat accelerated method has been achieved, and durability is yet to be investigated further in the coming months of the project. Are there any questions?
University of Edinburgh, and I'm researching circular economy for offshore wind, so I'm quite interested in low carbon concrete. Are there any practical issues with having to heat the concrete? I'm thinking about offshore wind where we need huge concrete structures, and how would heating work in that scenario?
Yeah, so it is important to sort of understand that we're not heating up concrete on site. We're not trying to accelerate, because this is not the issue. So essentially these low carbon compositions that I am investigating, they are proven to be working, and they essentially, technically, these compositions are conforming to the British standards 8500. So technically what it means, in very broad terms, that with few limitations, we could technically use it to replace the conventional concrete. But the problem is now that before we use it on site, we have to test it in the labs beforehand. And now, 3 months versus 28 days, it's just too long for any client to wait this long for the project to even start. So what we're trying to do, what I'm trying to do here, is to limit that 90-day to the minimum, essentially, so we can test in the labs as soon as possible, give the client the go-ahead, essentially, that, okay, this is, that composition will be sufficient for whatever you need, and this is the way how we accelerate the overall sort of timeline of the project, rather than waiting 90 days. Because the problem now is that the engineer is more likely to specify conventional concrete rather than the low carbon concrete, just because they can't afford to wait 90 days to even start the test, because we need to let concrete samples to develop maturity first before we even start testing, because otherwise we're testing on immature samples, it's not showing us anything. So low carbon concrete works, and it is durable, and it's been proven. There's tons of research on that, but it's the timeline that is the problem here. So what we're trying to do with my project is to limit that timeline to the minimum, so people can start specifying low carbon concrete more often, essentially.
Thank you. I've got a follow-up to
Yep.
that. Do you think the construction time, does that affect the construction time though, the 3 months?
So in my understanding, the project sort of phasing is already optimized to the maximum. So it is now being optimized to the 28-day sort of schedule, if that makes sense. So that 28-day testing time is already sort of optimized the whole time frame of the project. So regardless whether we can, I think what you're trying to, what we're asking is, like, why does it matter if we test it beforehand?
No, I'm asking if you're making things out of low carbon concrete and it takes 3 months to reach the maturity or the strength that you need.
Yeah.
Does that put a delay on projects, not for testing,
Not
but for
really.
actual construction?
No, because you can afford to wait 90 days, because for most projects, you don't really need the full maturity of concrete. So for example, if you can imagine a structure and a multi-story building, you cast one story, you wait for about 2 days for the concrete to develop the minimum of 10 MPa. I think that's the average strength, and then you can move on to another story. So that concrete, the first story, is still developing, but it's strong enough to support another stories as we go along. So what you're talking about is the early strength problem, which can be dealt with in the different ways. There is additives that we can add to a concrete mix, that sort of, for example, gypsum, that accelerates the initial strength, essentially, so the strength gain. So that's a different sort of problem, but it can be dealt with. There is ways of dealing with it. It's just, for now, what we're trying to achieve here is to, like I said, to minimize the process, but we worry that the performance might not endure, even though that we are matching the strength. It doesn't necessarily mean that we're gonna match the durability equal to the 90-day equivalent, because what we now are saying that, let's say, 12-day samples are okay. Then we've got the equivalency in strength, but we're now concerned whether the durability equivalency is there. Because if it's not, well, we can't confidently put it to the client after testing on the accelerated methods, being like, look, this is what will happen in 90 days. Because that's why we need to still investigate the durability issue of it. But we are hopeful that it will work.
Thank you.
I'm just wondering about the scale availability of the alternatives. So they're all byproducts from other processes. Are they available in a scale that can make a serious dent in the amount of Portland cement that's actually used?
So GGBS, as in granulated blast furnace slag and fly ash and limestone, they've been used for about 3 decades now. But there is another worry that we, as a country as UK, we don't produce that much steel anymore. We rather recycle rather than produce anymore. So we will eventually run out the finite amounts of the alternatives. There's still quite a few tons left, so we're fine for about 5 to 10 years. as what other research, different independent research papers say. But yeah, you're absolutely right. We will run out of that product eventually. And I know that there is some other research going on to eventually replace some of the, not replace, but being another lower, maybe not lower carbon, but lower carbon alternative to Portland cement rather than GGBS or fly ash, because we need to think ahead, because if you run out, what then? We can't just go back to Portland cement and produce however megatons of CO2 every year. So yeah, there is, I think the product is called calcined clay, or LC3. I think in America there's a lot of research on it.
I was just wondering if there is any long-term stability differences between both the cements, or are they both equally strong and stable?
Sorry, could you repeat the question?
Yeah. Is there any difference between the long-term stability in both the cements, old and the new one, or are they both equally stable?
So there is no fixed recipe for concrete types, as it were. There is, in British standards, there's over 36 cement combinations. So you sort of specify the concrete type to whatever you need. Whether there is some long-term issues with that, well, I'm assuming that if they've been introduced into British standards, my guess is no. But that could change on a very specific, on a very specific project, for example. That's why that's one of the reasons why you need to accelerate that period of time, because if, for example, we specify a concrete type and it doesn't sort of respond to whatever you would like in the out there on your construction site, well, we need to test another sort of composition of concrete, and then these, that time adds up. So we can't afford waiting 90 days. So that's the best case scenario, that we specify concrete and it will work and it's fine. But what if it doesn't, right? So if the shorter we go, the more sort of specifications we can go through. Does that answer your question?
Are there any other further questions? Okay, I have one.
Yep.
When your heat treatment at 50 degrees, I noticed some of them, the strength was higher than at 20 degrees. Was that just the limit in data, or was it actually a property?
Funny you should say that. This is another thing that we sort of noticed. So as you can, let me just go back to the descriptions, right? So whenever there is a fly ash involved, right, so these two, that one, the first one and fourth one, got fly ash in the mix. So they tend to keep going. So I'm actually kicking myself a little bit that I only cast so many samples and then stopped, because I run on the samples essentially at 20, I think that's at 29 days. Because it seems like it could go, go up further, which is sort of just rather than an interesting insight rather than any addition to my project. But I could specify some further work based on that, because whenever there is no fly ash, well, that just sort of levels off. There is a sort of asymptotic behavior here, but that keeps going, which is very surprising.
So do you have any understanding of the strengthening mechanism which fly ash provides to the concrete material?
So there's, with concrete hydration and complicated chemistry, there's different phases to it. So we know that fly ash starts to be reactive after about, I can't remember what it is. I think it's a week or 14 days, but after a while essentially, right? So it's sort of, that's why it, but that would align well with that theory here, because we know that roughly after, I think it's 7 days, it's sort of the fly ash phase sort of kicks in, and then that what sort of keeps the hydration going. Whereas with GGBS, that doesn't happen really. But this was known before that research, so this is just plays well with whatever we found. So that would explain why the concrete strength keeps growing with fly ash, because fly ash tends to do that, to sort of kick in the later phases.
Thank you.
Right.
Well, if that's all, I think give a round of applause to both speakers again. And that's the end of the shorter material session.